So good afternoon. Today we will start with the last two types of transforms. Okay. The first one is the Laplace transform and the second one is the Z transform. Before getting into the Laplace transform, let's have a recap of what we have discussed till now in the transforms, in the different transforms that have been used in digital signal processing. Okay. We started with Fourier series and Fourier transform, and over there we have seen that in these two types of transforms we basically analyze the continuous time signals. Okay. Now using the Fourier series we are able to analyze only the periodic signals. Okay. With the generalization of the Fourier series we got into the Fourier transform, and the Fourier transform was able to analyze both periodic signal and aperiodic signal or non-periodic signal. Okay. Similarly, when we went into the discrete time signal processing transforms, we had discrete Fourier series, discrete time Fourier transform, and we have also discussed about the discrete Fourier transform and using fast Fourier transform for the implementation of the DFT. Okay. So the discrete Fourier series and the discrete Fourier transform, they were analog to the Fourier series and the Fourier transform, which were meant to analyze the continuous time signals. Right. Now, in both these cases, what happened? Especially in the discrete time Fourier transform, we had frequency domain signals which were continuous in nature, and because of that, while we were implementing the inverse transform, we had to implement the integral function. Okay, that was one of the major disadvantages which cannot be carried out in the digital domain. Okay. So what we have seen is that because of this problem, the discrete Fourier transform, it came into existence, where both the time domain signal and the frequency domain signals, they have been discretized. Okay. Now the thing is that when we talk about all these Fourier transforms, so these are either Fourier series or the Fourier transforms. So what is the problem with this? The problem is that these signals, they were not capable of analyzing neither energy nor power signals. Okay. So Fourier series or the discrete Fourier series, they were able to analyze only the periodic signal, Fourier transform and discrete time Fourier transform, and also the discrete Fourier transform, they were able to analyze both the periodic and the aperiodic signals. However, these transforms, they were not able to analyze the neither energy nor power signals. Okay, so that was one of the disadvantages. Now, to overcome this disadvantage, what has happened is that we have to generalize this Fourier transform, and this generalization of the Fourier transform, it is regarded as the Laplace transform. So initially we started with Fourier series, we generalized it so that the Fourier series can be implemented for the aperiodic signal analysis also. So we got, due to the generalization, we got the Fourier transform. Now over here also, if you see, there are certain kind of signals that cannot be analyzed. Now to allow that, we have to generalize the Fourier transform again, so that we get to a new transform. In this case, it is the Laplace transform, which will allow us to analyze the signals and the systems which could not be analyzed using the Fourier transform because of its inherent problems which was associated with the Fourier transform, right? Now, no doubt, when we talk about the Fourier transform, it is one of the most robust transforms, and it has been commonly used in various fields, not only biomedical engineering, but also in other fields like, say, digital communication, talk about defense, you talk about geology, whatever field you can think of, right? But the thing is that, again, that they were, this Fourier transform, it was not able to analyze certain other uh, types of the signals. Okay. Now, when we talk about this discrete Fourier transform, so what is happening? We have digital frequency which is given by omega. Okay. Now, when we have this another frequency, this thing omega, this which is having a sign of ohms, it is related to the analog frequency. So when we are talking about this discrete Fourier transform, we may have the digital signal, we may have the analog signal, and we have already discussed about what is the difference between a digital signal and an analog signal. Okay, a discrete time signal can be a digital signal, it can be an analog signal. So in the case of analog signals, the frequency is given by this omega, okay, uh, which is in the form of or in the sign of ohms. On the other hand, the digital frequency, they are being given with the omega, which which is similar to that of W. Okay, so when we are getting into this filter designing and filter and introduction to different digital signal processing techniques, these two conventions, these two, analog frequency and the digital frequency, will very commonly be used. So please keep these notations in mind. When we will be using analog, then we will be using the first omega, and when we will be using the digital frequency, we will be using the second omega. Okay. Now, when we are talking about this Laplace transform, it is given by the differential equations. Okay, it is given by the differential equations. On the other hand, when we implement Z transform, what is Z transform? It is nothing but, it is an analog transform of the Laplace transform, wherein we can design digital systems. Wherein we can design digital systems. Okay. So in using the Laplace transform, we will we are capable of designing continuous time signals and systems, or continuous time systems. On the other hand, Z transform, it allows us to design digital systems. Okay, so in the digital system, what happens? This differential equation, it is being represented in the form of difference equation. So dy, it is given by yn minus yn minus 1 and xn minus xn minus 1. Okay, so this is backward difference method. Okay, so we are taking this instance and the previous instance values to calculate the dy by dx. There is another forward difference method where we use the future values. In that case, it becomes y of n plus 1 minus yn divided by x of n plus 1 minus of xn. You getting my point? So, however, we have discussed that LTI systems, they are basically causal systems, and since they are causal systems, we will not be interested in the forward difference method. Okay, we will only be interested in the backward difference method, right? Any doubt till now? No? Good. So, in Fourier transform, our operator was j omega. Okay, our operator was j omega. While we are designing or developing the Laplace transform, this Fourier transform operator, it is being replaced with S, which is regarded as the Laplace operator, and it is given by sigma plus j omega. Okay. Now, why this is so? If we look into the Fourier transform equation, capital X of j omega, it is equal to f of x of t, which is the time domain signal, integration of minus infinity to infinity, x of t e to the power minus j omega t. So this is the basic Fourier transform equation. Okay, and the next one, it is the inverse Fourier transform equation. Now what happens if a signal, it is going out of bound? So can we analyze? Because at time tending to infinity, what will happen? If a signal is going out of bound, so the amplitude will also be going out of bound. Okay, right? It will be ever increasing, and at time tending to infinity, you will be having amplitude tending to infinity, which defies our Bibo stability criteria, right? Which defies our Bibo stability criteria. Now, because of this, how can we analyze these signals? The simplest thing is that we multiply the signal with a signal component given by e to the power minus sigma t, where sigma is a real component or a real number. So at time tending to infinity, what would be the amplitude? Amplitude would be tending to 0. Now, even if you are having an ever increasing signal, if you are multiplying with a value which is tending to 0, it will be near to 0. That means it is getting finite. Okay, the amplitude is getting finite. So that is what it has been done over here. If you see, instead of this Fourier transform x of t, if we multiply the signal with e to the power minus sigma t, we get xt into e to the power minus sigma t, and within over here also, if you see, xt has been replaced with xt multiplied by e to the power minus sigma t multiplied by e to the power minus j omega t. We have just taken this and we have put it wherever we were having xt. Okay, so we got a parameter, integration of minus infinity to infinity x of t e to the power minus sigma plus j omega. What we call this? We call that as s. Okay, so we get to this equation. Similarly, if you look in over here, what happens over here? X of t multiplied by e to the power minus sigma t, for the inverse Fourier transform, you do it. So you will be getting these equations. Okay. Now, since S is equal to sigma plus j omega, if you try to differentiate it, we get d of omega, it is equal to 1 by j into ds. Okay. So you replace this d omega value over here. So when we do it, we get this inverse Laplace transform x of t equals to 1 by j 2 pi integration of minus infinity to infinity x of s e to the power st ds, and the Laplace transform, it was basically x of s equal to integration of minus infinity to infinity x of t e to the power minus of st dt. Okay, so these two are the Laplace transform equation here. Okay, so forward Laplace transform and the inverse Laplace transform. So like in the Fourier transform, over here also we will have this convolution integral. Okay, so all the parameters that we have discussed in the this convolution in the previous class, that also applies over here also. Okay, so initially when the systems were being developed, these systems were developed in the continuous time domain. Okay, so when we were talking about these systems or the filters, we were basically discussing about the systems that can handle the continuous time signals and systems, right? Now, what happens is that all the understanding of the continuous time systems, they are being taken to develop the digital systems. Okay, so whatever the knowledge we were having from the continuous time systems, that are being taken and they are being applied into the digital systems. So understanding the system criteria, it is of utmost importance in the case of this continuous time signals. Okay, so we need to, what I mean to say is that we need to understand what are the stability criteria for designing a continuous time systems. It is of utmost importance for us if we want to develop the digital system. If we don't have an idea about the continuous time systems, we will not be able to develop the digital systems. Okay, so there is a what you call fact which says while designing stable filters, why poles are placed in the left hand side of the Laplace transform plane. Okay, when we talk about this Laplace transform plane, so what we are basically doing is that we are having a 2D plane, and in the 2D plane we have sigma in the x-axis. What is the sigma? Sigma is the real component which we have discussed or included in the Laplace operator. And this y-axis, it is basically the j omega. Okay. Now this is a 2D plane. Now this plane, it is being divided into three parts. One is left hand side plane, right hand side plane, and the j omega axis. Okay, and the j omega axis. When sigma is equal to 0, where are we? We are on the j omega axis. So if you come over here and if you put sigma equals to 0, this component becomes 1, and what we do? We go back to the Fourier transform. So in the Laplace transform, where the Fourier transform exists? In the j omega axis, right? In the j omega axis, Fourier transform exists. So when we talk about Fourier transform, we only talk about frequencies. What are the frequency components? So all the frequency components, they are present on the j omega axis. Okay. So now you would say, what are these poles? We discussed about some amplifiers, right? So we have a system whose gain is given by A, and we are having X as the input, Y as the output. So what we said is that gain of the system, it is given by Y by X. Okay. So V0 by Vin. So V0 is the Y, Vin is your X. A is the gain. And if we make it frequency responsive, then we call it transfer function H of S equals to, say, Y of S by X of S. So this is the transfer function, and this, due to the presence of this S operator, the system is basically frequency responsive. Okay. Now when we talk about this Y of S and X of S, they are nothing but polynomials, polynomial function. Okay. And what does polynomial functions have? They have roots. Class 11, 12 में you must have solved na polynomial function by partial differentiation and all these things. right? So they have roots. Huh? Transfer function is basically the impulse function. Okay. Here. So they have roots. Roots means you have solutions. Solutions means to find out some solutions. Suppose there is a polynomial function s minus a multiplied by s minus b multiplied by say s minus c. So if you want to find out the solution, where would be the solution? At s equal to c, at s equal to b, s equal to a, you will be having all the solutions. So when s is equal to c, this component will become 0. Okay. So when s equal to b, this component will become 0. And when s equals to a, this component will become 0. That means at those particular values, the polynomial function, it will have a value of 0. Right? It will be having a value of 0. And how do you find out? You do this thing, you put it in the form of the multipliers equals to 0. Then you find the solutions one by one. Right? Now at these locations, wherever the solutions are, say for example, if the if you are considering the solutions of ys, how it will affect the transfer function? Directly. That means at those particular points where you have the solutions, the value will become 0. So these solutions, they are basically existing on the Laplace plane, and since they are being present on the Laplace plane, at those points you will be having an amplitude of 0. What is transfer function? It is gain. Gain किसको बोलते हो? Suppose you are doing input in comparison to the input, uh, how much increment you have got. Okay. Now over there the gain would become 0. So the solutions of ys, that is the numerator, they will put the transfer function values to zeros. Hence these solutions, they are regarded as the zeros. Hence these solutions, they are regarded as the zeros. Similarly, if you consider the x's, what will happen to the h's values when you have these solutions? Infinite. Infinite means there will be a steep rise in the thing. So it is equivalent to a pole. So the solutions of the denominator, solutions of the denominator, they are regarded as the pole, because at those frequencies the system will have the capability to take the gain of the system to infinity. So getting my point? हाँ ना क्या बोला? हाँ बोल के सर ऐसे नहीं हिला रहे हो. So poles and zeros concepts, they are clear now. So while we design and a continuous time system, we need, there are some criteria for the placement of the poles and the zeros. Okay. So before going into the digital systems, we need to understand those criteria. Okay. The first criteria is that if you look over here, the first criteria is why poles are always placed in the left hand side of the Laplace transform plane. Okay. So you look into this equation, it is very familiar to you. It is the Laplace transform equation, right? So S is a complex variable, sigma is the real part, and omega is representing the imaginary part. Now, relation between poles and system stability. A system is considered stable if its output is bounded for any bounded input. In mathematical terms, the system's impulse response ht must tend to 0 at time t tends to infinity for the system to be stable, which is basically the Bibo stability criteria we have been discussing. The behavior of ht is closely related to the position of the poles hs in the complex plane, right? Now, poles in the left half of the S-plane, when poles are located in the left half of the S-plane, the sigma value is less than 0. The sigma value is less than 0. So what happens? The impulse response of the system includes the term like e to the sigma t, where sigma is less than 0. Since sigma is negative, sigma t tends to 0 at time tending to as the time increases, ensuring that the impulse response ht also tends to 0 over time. You're getting my point? Because the value of sigma it becomes negative, so it is capable to put down the original signal component to a value near to 0, or we can say that the amplitudes are kept within bound at time tending to infinity. Okay? Anyone who has not understood? Everyone? Okay. So, on the other hand, if you place the pole on the right hand half of the S-plane, sigma is greater than 0, positive value है, e to the power sigma t, it is also going out of bound, you cannot do anything. So, even if it, even if the signal is bounded, the e to the power sigma t component, since the value is greater than 0, it will take the output to infinity. ब्लैंक लुक क्यों आ रहा है? ओके, सो इसी के ऊपर पूरा कॉन्सेप्ट बेस है. इफ यू आर नॉट अंडरस्टैंडिंग यू मे जस्ट स्टॉप मी एनीवे. सो this is the thing. Then the next thing is poles on the imaginary axis. Poles on the imaginary axis. So what will happen? Over there, sigma equals to 0. Okay. Now, impulse response include it was j omega t. Okay. So if you try to find out this modulus, it is basically a combination of the sinusoid sigma sine of omega t plus j cos omega t, right? So you are having this thing, so it is basically a combination of sinusoids, so you are having this oscillation, so the amplitude it oscillates. Now since they are oscillating, so what happens when the poles are being placed at sigma equals to 0, that means on the frequency axis the system becomes marginally stable, where the output neither grows nor decays but remain oscillating. Okay. Practical implications in filter design. In practical filter design, ensuring that all poles are placed in the left hand side of the S-plane is crucial for achieving a stable filter. This is particularly important in analog filters and control systems where stability directly impacts the performance and safety. Digital filters which use the Z transform have similar requirement where poles must be inside the unit circle of stability, analogous to the left hand side condition in the Laplace domain. So we will be discussing about the Z transform in few moments of time. So there we will see, because as I already told you, we are hiring the stability criteria from the Laplace transform and then we are implementing it in the Z transform for designing the digital systems. Okay. So while designing stable filters, why zeros can be placed anywhere in the Laplace transform. Okay. So the thing is that understanding the zeros in the Laplace transform. So mathematically, if f is equal to s of 0, then h of s0 is equal to 0. That means the system stays within the bounded limit. Okay, it is not going out of bound. So wherever you place the 0, the solutions will lead to a bounded output. Okay, so impact of zeros on system stability. Pole determines the natural frequency response of the system. By particularly its stability, its system stability is dictated by whether its poles are located in the left hand side of the S-plane. Zeros on the other hand affect the frequency response of the system. They determine which frequencies are attenuated or eliminated by the filter. Okay. Zeros can be placed anywhere in the complex plane without affecting the stability of the system. As I told you, the solutions to these roots, they will bring the transfer function down to 0. So because of that, wherever we place the zeros, there will be no stability issues. Okay. Why? Because they do not contribute to the exponential growth or decay of the system's response. Okay. Zeros and frequency response. Zeros on the imaginary axis. These zeros cause certain frequencies to be completely attenuated. For instance, a 0 at s equal to j of omega naught will attenuate the frequency component omega 0. Okay. Zeros in the right hand plane can introduce phase shifts and change in the system's transient response, but do not cause instability. Zeros in the left hand plane, zeros in the left hand plane generally lead to smoother and more stable frequency responses. Okay. So role of zeros in system design. So zeros are used to control the passband and stopband characteristics of the filter. Okay. So why zeros can be placed anywhere? I have already discussed, because it is not affecting the stability of the system. Okay. In practical filter design, zeros are chosen to achieve specific filter characteristics such as eliminating unwanted noise or emphasizing certain frequencies. The next one is designers may place zeros in position to optimize the filter's performance for the intended application without worrying about introducing the instability within the filter. Okay. So these are the practical implications of placing the zeros in the Laplace transform plane. Over here, I have used certain things which you will not understand at this moment, but as we delve into the this filter designing aspects, you will find, or you will be able to correlate what I have discussed today. Okay, maybe in a couple of classes time, we'll be able to get into that. Now coming to the Z transform, you need to understand the Z transform over here. So what is Z transform? Z transform is given by this equation: x of z equals to summation of n equals to minus infinity to infinity x of n z to the power minus n. Okay. So basically what it says is that if you are having xn, then if you multiply with z to the power minus n and add up for all the n's, then you will be getting the z transform of xn. Okay. Say for example, our xn is given by 1, 2, 3, 4. So the xz, it will be given by xz equals to 1 into z to the power minus, what is the n value over here? 0. True. Plus 2 into z to the power minus 1 plus 3 into z to the power minus 2 plus 4 into z to the power minus 3. So see how conveniently I have converted the xn into a complex plane xz, which allows us to analyze the digital filters. Okay. Similarly, if you are having yn, if you want to find out yn, so how you can find out? Yn is equal to h of z multiplied by z to the power n. Okay. So this is the equation for an LTI system. Okay. Herein our hz, it is given by summation of n, hz is equal to summation of n equals to minus infinity to infinity h of n into z to the power minus n. Okay. So this generalized equation, it is regarded as the bilateral z transform of xn. Okay. Now the thing is that when you talk about this minus infinity to infinity, we have already discussed, we are not discussing about the negative time information. Okay. So since we are not discussing about the negative time information, that means we are interested in n equals to 0 to infinity x of n z to the minus n, and this equation, it is regarded as unilateral z transform. It is regarded as unilateral z transform. Okay. Now relationship between the z transform and the Laplace transform. Let's see what is the relationship. Suppose this is the xt equals to x cap t equals to summation of n equals to minus infinity to infinity x of nt into delta t minus nt. What is this delta t minus nt? We have already discussed impulse train. Okay. So this is the thing. Now if we take Laplace transform in both the case sides, we get x of s equal to summation of n equals to infinity x of nt multiplied by e to the power minus nst. On the other hand, if you look into the z transform, we have xz equals to summation of n equals to minus infinity to infinity x of n into z to the power minus n. Now if you compare these two equations, Laplace transform and z transform equation, we can easily say that z is equal to e to the power st. Okay. Z equals to e to the power st. Okay. But we know s is equal to sigma plus j omega. Therefore, z is equal to e to the power sigma plus j omega t. So we can segregate this e to the power sigma t multiplied by e to the power j omega t. Right. So modulus of z, it will be this real value, and phase of z, it will be the omega t. Okay. Now when sigma is equal to 0, that is we are on the frequency axis, we get modulus of z is equal to, when sigma is 0, 1. So in a plane, in a 2D plane, we will be having a radius, a circle, sorry, we will be having a circle having a radius of 1. So this is the implication of this thing. Now when we have this, so we can see the frequency axis, it has been mapped onto the unit circle, because modulus of z is equal to 1, right? Modulus of z is equal to 1. So we are on the unit circles, right? We are on the unit circle. Now when sigma is less than 0, we will be within the unit circle. When sigma is greater than 0, we will be outside the unit circle. Okay. Achha, e to the power j omega t, somewhere I told sin omega t plus j cos omega t. So it is the other way around, cos omega t plus j sin omega t. Okay. So please correct it in your notes. So what we have is that This S plane, it is getting mapped into the Z plane, okay, where our unit circle, on the unit circle, we are having the frequency axis. So what is our X and Y axis? X axis is real Z, imaginary Z. Real Z and imaginary Z, and frequency is on the unit circle. Okay, so this is one of the questions in comprehensive Viva. Where is the frequency axis in the Z? And till now, believe me, 99% of the students, they forget these concepts and they are not able to answer this. So if your basics are clear, you will be able to answer. Okay. So, but when we are doing this, mapping, there is a problem. What is the problem? Problem is, here the analog frequency, it is starting from minus infinity to infinity. Let us start with 0. Okay. Let us start with 0. So we are having this 0 here. Then you are again coming back to 360 degree. That is 0. After that, what will happen? Other frequency components will also be mapped onto this unit circle. Right? Other frequency components will also be mapped into unit circle. So in Laplace transform, we were having one-to-one mapping of the frequency component. So one point was getting one frequency component, right? Whereas in digital signal processing, when you try to design any system, you will be having multiple frequency components mapped to a single point. Okay. So how do you take care of this? How do you take care of this? The thing is that if you come to this slide, if you look into the signal x cap t, we are having two components, x of t and x of t minus mt. So we have a frequency related to xn, and when we sample the signal, if you remember, we discussed that we band limit the signal. Okay, when we try to go for the sampling of the signal, we band limit the signal. That means we restrict the signal frequency components. So if we consider the maximum frequency of a signal to be FM, lowest would be 0. So the frequency component would be 0 to FM. Okay. Then you will be having, apart from this frequency component, you will be having another frequency component. When you are talking about impulse train, you are having impulses, right? What about this? Repetition of impulses are happening, right? You are having this repetition of the impulses, and when you are having the repetition of the impulses, why you are doing it? You are doing it for sampling the signal. So that is called the sampling frequency. That time duration related with the sampling, it is regarded as the sampling frequency. Okay. So we'll be having two important parameters. The first one is the FM associated with frequency component of the signal, maximum frequency component of the signal after band limitation, and the second one is the sampling frequency. So which one is higher? Sampling frequency is always higher. Okay. So there is a criteria called Nyquist criteria, where we say Fs is greater than equal to 2 of Fm. So since we are having the maximum frequencies in maximum frequency of Fs, when we have both the Fm and Fs, so the Fs would be the highest here. So Fs assumes the highest position. Highest position, which one? Where we have at 360 degree or 0 degree, whatever you say. So where would be the Fm? If you consider the limiting case, Fs equals to 2 of Fm. So Fm equal to Fs by 2. This is the limiting case. Okay. So when we have a specific sampling frequency given, and for a particular system, digital system, so the maximum frequency components that can be legally processed through that system would be Fs by 2. Okay, it would be Fs by 2, and this equation, it is called the Nyquist criterion or Nyquist equation. Nyquist criteria or Nyquist equation. You're getting my point? Now, two pi. So we are having only this 0 to 2 pi components we are only having. Okay. So if your frequency component, it lies between 0 and pi, what happens? These frequency components, they also replicate in the pi to 2 pi region. Why? In DFT we discussed, when we sample the signal in the time domain, the signal becomes periodic in the frequency domain. Okay. So basically you are having the same signal components of 0 to pi in the pi to 2 pi components. So if you see the over here 0 to pi, we are having maximum frequency over here, and at the same time we are having the lowest frequency over here. Okay. So if you do not take proper care, what will happen? The low frequency components, they will be interacting with the high frequency components, and your signal will become distorted, and this distortion, it is called aliasing. This distortion, it is regarded as aliasing. So once a signal is aliased, that means it has already been distorted. You do whatever, you will not be able to get back the original signal. The only and only way to prevent aliasing is to increase the sampling frequency. Okay. Why? Because suppose you are having 100 hertz sampling frequency. So over here you will be having 100, here 50, this is 0. Now you make it 200 hertz. You make the sampling frequency 200 hertz. Now what happens? Here at pi, we will be having 100 hertz and 0. Now what will happen? Somewhere at around pi by 2, your FM will be restricted. Similarly, over here also, you'll be having this component. Now, if you see, there is a dead zone, dead buffer zone. Okay. So, by introducing this dead buffer zone, you will be able to restrict LERC. Okay. And when I say that the Nyquist criteria is says Fs should be greater than equal to 2 of Fm, this is because the limiting case is 2 of Fm, but if you try to procure the signals using the low cost data acquisition systems in the lab, we have seen that this equation becomes 10 of Fm. The reason being, when you use low cost systems, you are using low quality components for making the low cost system. Okay. Higher you pay for a device, the better will be the performance. Okay. So if you are having low cost items as a data acquisition system, so low cost data acquisition system will be having low cost component inbuilt over there. So their non-idleness will be much higher, and since their non-idleness will be higher, because of that, what will happen? There will be some this aliasing incorporated into the system. Okay. So under practical considerations, we have seen that it becomes for low cost systems as Fs equals to 10 of Fn. However, if you go abroad and do some kind of research, or if you go into the industry, they use very high quality system. Over there, you may go up to say Fs equal to 3 of Fm or something like that. Okay. So you can come closer to this thing. The main problem with higher Fs is that you will be having per second a large number of data. Yeah, right. So suppose you are having a sampling frequency of 1 hertz. So per second you will be having one data. And if you are having 10 hertz sampling frequency, you will be having 10 data 1 second. So if you go for 100 hertz sampling frequency, you will be having in within 1 second 100 data point. So it's a lot of data point. So it becomes difficult to process those data because computational burden it increases. Okay. Now the relationship between Ft and Z transform, again by the analogy of the Laplace transform and Ft, and again Laplace transform and Z transform, we know that x of e omega, that means on this unit circle the Fourier transform exists. So it will be in the range of 0 to pi. The Ft exists in the range of 0 to pi. Thereafter, after pi to 2 pi, again the same thing repeats. Okay. The discussions are given over here, how we got to this equation. You can just go through that. It's quite self-explanatory. So aliasing, definition: aliasing occurs when a continuous signal is sampled at a rate that is insufficient to capture its variations accurately. According to the Nyquist-Shannon sampling theory, to avoid aliasing, a signal must be sampled at a rate that is at least twice its highest frequency component, okay, which is also regarded as the Nyquist rate. So aliasing happens when the sampling rate Fs is less than twice the frequency, the highest frequency F max of the signal. The frequencies is higher than Fs by 2 are indistinguishable from lower frequencies and appear as aliases at incorrect frequencies in the sampled signal. Okay. In fact, the original high frequency components of the signals are folded back into the lower frequency range, causing distortion. This results in the misrepresentation of the signal's frequency content. Okay. So, example, I have already discussed about the example. Okay. Now, over here, if you see, when a signal xt with a frequency f is sampled at fs, the sampled signal is xn, xt sampled at t equals to nt, which is equal to x of nt, where capital T equals to 1 by fs, which is basically the sampling period. If f is greater than fs by 2, the frequency component at f will appear as f dash, which will be equal to modulus of f minus k of fs for some integer k, causing an alias. Okay. Then there is another term which is regarded as the spectral leakage. So what is spectral leakage? Students do mistake over here. Spectral leakage is nothing but it occurs when a signal spectrum is spread out over a range of frequencies rather than being confined to its two frequency components. This typically happens in the context of discrete Fourier transform when the signal is not an integer multiple of the fundamental frequency of the DFT. So what I want to say is that suppose you are having a sinusoidal signal, then you are time limiting it. So what happens if you go for normal response, original response at a particular frequency, you will be getting the signal. Okay. However, when you are applying some window for truncating the signal, because we talked about DFT and all these things, what we are doing? We are having a continuous signal, but we are truncating that because when we talk about 8-point DFT, we can take only 8 points signals, 8 components from the signal. We cannot take more than that. So we are basically abruptly truncating the signal, which is also regarded as the windowing. Okay, and when we are doing the windowing, so what happens is that we get, apart from this spectral component, the peak, whatever we get over here, if you look over here, so this is the original peak, and apart from that, we are also getting the spectrum which are being distributed across the frequency components. So this is called the frequency or this spectral leakage. Okay. So there is a difference between the aliasing and the spectral leakage. Okay. Spectral leakage happens during the windowing process. Okay. So these are the key differences between aliasing and the spectral leakage. So you can just go through that. So with this we complete this whole chapter.